Hi, welcome to Physics Teacher. In this video, I'm going to go over the last problem in the Cayley Math Contest of 2020, which is a grade 10 math contest, and it is a challenging problem. Give it a try first, and I'll be right back with the answer. Alright, in this question, we're looking at how many positive integers equal to or less than 20,000 have the property that 2n has 64 positive divisors and 5n has 60 positive dividers. Alright, so whenever you're doing one of these contests and it asks you to look at the number of divisors, it's really helpful to look at the prime factorization. Prime factorization is just looking at every positive integer greater than 1 that can be written as a product of prime numbers in a very unique way. For example, I can take the number 1,500 and write it as 2 squared times 3 times 5 cubed. So 2, 3, and 5 are all prime numbers. And that product will be equal to 1,500. So this is what we call prime factorization. Now let's say we have another number, let's call it d. Let's call this one, for example, m. If d is some sort of divisor of m, and we were to determine the prime factorization of d, turns out that the only possible prime factors of d are the same prime factors of m. So in this case, it would be 2, 3, and 5. Now the exponent would have to be either equal to or less than the exponent that you see in m. So this one could be either 0, 1, or 2. This one could be 0 or 1, and this one could be 0, 1, 2, or 3. Based on this, if we write n as some prime factorization, now we don't know what n is, but let's write it as, say, some prime number p1 to the exponent of some positive integer a1, and then p2 to the a2, and so on, and so on, and so on, all the way up to some maximum pk to the ak. Well, we can write d as some divisor of that, where d is going to be the same prime number to the power of b1 times the second prime number to the power of b2, and so on, all the way up to pk to the power of bk. Now if we look at this, you can see if this is 2, this has 3 possibilities. Right? If this is 1, this has 2 possibilities. If this is 3, this has 4 possibilities. This means that for B1, there are A1 plus 1 possible values. And similar for B2, there are A2 plus 1 possible values. And since every combination of these possible values gives a different divisor d, then we could say that there are A1 plus 1 times A2 plus 1 all the way up to AK plus 1 possible divisors. Now what I'm going to actually do is write n as p1 I'm going to say is 2 to the power of some value r, and p2 I'm going to say is 5, some value s. And the reason why I'm choosing 2 and 5 is because 2 and 5 are going to play important roles since I'm looking at 2n and 5n. And then times by some third prime numbers to the power of a3 times p4 to the power of a4, and so on, all the way up to some maximum prime to the power of ak. Now what this means is then 2n would have the following divisor. Since it's just twice n, it would be the divisor of 2 to the r plus 1. And then the rest would be the same. 5s times p3 to the a3, and so on, all the way up to pk to the ak. Now the same goes with 5n. it's going to be the same as n, except the exponent for 5 is going to be 1 more. So we got 2r times 5 to the s plus 1 times p3 to the a3, and so on, all the way up to pk to the ak. Now if we go back down to this concept here, and we were to look at all the possible divisors for 2n and 5n, well, for 2n, what we have is r plus 1, like here, a1, plus 1. So that gives us r plus 2. And then we have the s plus 1. We have to add 1 to each exponent and multiply them to give all the combinations of possible divisors. So we have s plus 1. And then a3 plus 1 times a4 plus 1, all the way up to ak plus 1. And that is going to equal, as they say, there are 64 possible divisors. All right, and I can do the same for 5n. So that's going to leave us with r plus 1 times s plus 2 times a3 plus 1, and so on, all the way up to ak plus 1. And that'll all equal, for our 5n, we have 60 possible divisors. Now notice that in both of these equations, inside these lines that I've just drawn are the exact same things. These are going to be the exact same. And so why don't we look at a common divisor for 64 and 60. So 64 has the following divisors. It can be 1, 2, 4, 8, 16, 32, or 64. Now 60 has the following possible divisors: 1, 2, 4, 5, 6, 10, 20, 30, and 60. So the only ones we have in common here are 1, 2, and 4. That means the product of what I have in the bracket here must be equal to either 1, 2, or 4. So we're going to have to analyze each case, where it equals 1, where it equals 2, and where it equals 4. Let's start with case number 1, where we'll look at when it equals 4. Case 1. Now the only way for this product of positive integers to equal 4 is, let's say the first two terms are equal to 2, so 2 times 2 give us 4, or that first term is just equal to 4. Now going back to these two equations that we had before, if I substitute 4 in for the product of these integers, I can rearrange, divide both sides by 4 to get the following equation. R plus 2 times s plus 1 will be equal to 16. And I can do the same thing in our second equation, where I substitute that entire product as 4, and I'll get r plus 1 times s plus 2 will be equal to 15. Now let me rewrite these equations, 1 and 2. Give myself some room and we'll solve the system. So first I'm going to FOIL each side. So that's going to give us rs plus r plus 2s plus 2 is equal to 16. And I'll do the same with equation 2, which gives us rs plus 2r plus s plus 2 is equal to 15. Now what I'm going to do is take equation 2 and subtract equation 1. So notice that the first term in each equation is going to cancel when I subtract them. Then I'll have 2r subtract r, which is just r. And then I'm going to have s minus 2s, which is minus s. And 2 minus 2 will go away. And 15 minus 16 is negative 1. So rearranging, I can say s is just going to be equal to r plus 1. Now I'm going to take this value here for s and substitute it back into equation 1 up here. So that's going to give us r plus 2. And then s is now r plus 1. And then I have this plus 1 again, is all equal to 16. Well, this is r plus 2 and this is r plus 2, so that is giving me r plus 2 squared. And that is going to be equal to 16, which is the same as 4 squared. And since we know that r must be a positive integer, this leads us to the fact that r is going to equal 2. And since r equals 2, if I look at this equation again, we can see that s is going to equal 3. Alright, so let's go back and look at our previous equation. I'll just rewrite it here, but we had n written as a prime factorization of 2 to the power of r times 5 to the power of s, and then we had some other values, p3 to the a3, and so on and so on and so on, p4 to the a4 all the way up to k. But now what I know is that n is going to be 2 to the power of r, where r is 2, 5 to the power of s, where s is 3, and then we had the option where a3 plus 1 and a4 plus 1 were both equal to 2 in order for this to equal 4. So we had a3 plus 1 was equal to a4 plus 1, which is equal to 2. And that would mean that both a3 is equal to a4, which is equal to 1. In that case, if both a3 and a4 were equal to 1, then we would have some prime, let's call it p3, don't know what it is, but it would be to the power of 1, times some other prime also to the power of 1. Then we also had the case where just a3 plus 1 was equal to 4 on its own in order for this to be true. And if that's the case, then a3 would be equal to 3. So another possibility then for n would be 2 squared times 5 cubed times p3 cubed. Now you can look at cases 2 and 3 where these values are 1 and 2. And I encourage you to do that. But what you'll find is that there are no possible values for r and s where that's going to work out. So let's just continue on with this to see how many possible values of n we actually have. So this value is 500 p3 p4, and this value here is 500 p3 cubed. Now since we know that this value must be less than or equal to 20,000, if I divide both sides by 500, I know that p3 p4 must be less than or equal to 40. And the same goes with this. I know that p3 cubed must be less than or equal to 40. So how many possible cases are there? If we look at this one here, and we were to take two prime numbers that are not 2 and 5, and find their product to be less than 40, how many possibilities are there? Well, we could take 3 and 7, and the order doesn't really matter. 3 and 7 will give us 21. That's less than 40. 3 and 11, that'll give us 33. And 3 and 13 will give us 39. So that is 3 possibilities right there. And those are the only possibilities. And for this one here, the only possibility is 3 cubed. 7 cubed is going to be way over 40. So that's one possibility for a total of 1 and 3, 4 possibilities. Our answer is A.